So this is a very fast video on topology optimization for the VATRE project. My name is Sebastian Estivill. I am an engineer and a master in disaster management administration. So I'll try to be as brief as possible. The purpose of this video is for the 2022 class for the Tecnológico de Monterrey, and this is their graduation project. So I want to start by acknowledging that nature is constantly designing and redesigning itself, and we as human or living things are subject to that process. Actually, every living creature in this planet is subject to that process, and it is based on survival. Like what I will introduce certain principles that I think are fundamental to understand what topology optimization is and how to execute it properly. So this is a disclaimer to this point would be this is not a video about how to do topology optimization in any software. This is basically on how the thinking should be, or at least what I have come to realize the thinking should be on topology optimization. So nature is a bit hard, and basically if you're fit to survive, you keep on going and your genes keep on going in this timeline of life. If your genes are not fit to survive, then you die and you don't leave that genetic information, so you go extinct. Basically, it is as simple as that. So we're going to take that principle and apply it to topology optimization. And that's what I meant by evolution. It is the sense of iterating new generations which can adapt to new environments or which can fulfill certain constraints, and those constraints will be able to optimize their way around whatever task they're meant to do. And this is the tricky part when people don't really interlink what nature does and what we do in engineering. So people oftenly ask me, well, how can you apply this like for a table or for a chair or for a fridge? And that's basically what I want to solve with this video. The second principle is what I like to call clay. And what I mean by clay is that topology optimization is kind of like a sculpting process. The machine will iterate every possible volume that can fulfill certain conditions, and if that volume is not subject to a certain stress strain condition, then it will erase it and reiterate a new geometry, and so on and so forth, until it finds the best geometry using the least amount of material that can fulfill those stress conditions. And that's, of course, the third principle, stress-strain. I will not go deep into this, but I will assume that people watching this video are familiar to stress-strain diagrams and everything that is like related to them. So let's jump into the VATRE project. This is something that I did extremely briefly for the purpose of this project, and that goes for our first iteration. So what you can see in the upper part, the two figures, it's a trimetric view and a lateral view of an initial guess that I have. And what I'm trying to build here, I'm trying to build an arm, a leg, or like, yes, a leg for a drone. And in this case is the VATRE drone. So I'm building material that it is meant to, like, I'm building clay that the machine will use to sculpt. Then I'm using a software, and that software will create those iterative conditions and will give me an initial result. So the lower part is the result that the machine gave me. It looks organic, it looks strange, it certainly has less material. To be precise, it has 80% less material than the upper part, but it's not really looking quite like a drone. And you might ask, well, this doesn't look at all like an arm for a drone. Well, the big circle in the middle, it's supposed to be where the chassis, where all the components are. So that will be the core, the body of the drone, and the extremities where the rotors are. That's where the engine is supposed to be. And I'm applying certain forces to these two surfaces, and I'm trying to see how the material behaves, how the iterative process behaves. So based on the results given by that, I will change the forces and I will treat a second iteration. Basically, with the same material that I used for the first iteration, now I'm simply applying different forces to it. And now it's getting to look a bit better, but it's not quite what we're looking for. So I will create a second guess. Well, actually, this is how it looks like a drone. I take that one arm, and then I make in my CAD software, I revolve it around itself 6 times, creating a hexacopter. So, but it's getting there, but it's not quite what we're looking for. It's chunky, it's certainly not quite aerodynamic, and it looks heavy. The third process would be, okay, well, I have a second guess. I'll try to build a new clay geometry. I will have a new volume of iterations, and I will apply other forces. So as you might have assumed, the thicker part to the right, it's where the drone will be connected, and to the left, it's where my rotors are. And I'm applying certain forces, and this is what the machine is telling me. Again, it is not quite what I'm looking for. Then, again, that's how it looks like from a side view. Then that's exactly what I wanted to go through. I take the process of my first, second, and third iterations mentally, and I start to make more accurate guesses. And this is what I find. A geometry that looks organic, that looks light, that looks aerodynamic, and that can fulfill the purpose of my optimization. And the lateral view, of course, and this is something that looks way better and something that I might expect. So I am assuming many things here, and I'm jumping ahead many steps, but the summarized version of this is how I'm jumping mentally in my thinking on how to establish the forces, how to set the proper conditions for the machine to be looking for the right things. And that's also something important. The reason I'm doing one leg at a time is because, first of all, to save power, to save computational power. Otherwise, each process will take days, and when I am doing only one leg, each process takes me at least 2-3 hours based on the machine that I have and based on the modifications that I'm doing. So this was done basically in one day. So it's not something fancy. And it's completely arbitrary. It's just to show the tool or the mental tool. The other thing that it's very important to establish on this video, and I should have done that first, is the purpose of this video is for you, my students, to go through the process. This is not meant to be as a guide, like, okay, like a cooking recipe. No. This is just a superficial guide for you to get like a spark on how the creative process should be. And that's basically kind of what nature is constantly doing. Nature is exploring possibilities on how things can work. Let's call them mutations. And if the mutation works, it survives, and the gene transcends, and that animal or that living thing evolves. If that mutation is not helpful, then the animal will extinct. But what is functional for mutation is that if it can adapt to the new environment or to a certain condition, then it will prevail. I'm not getting into the details on how other things regarding this topic works, and of course we humans, we have been changing the environment a lot, so animals are not being able to adapt as fast as we are changing their environments. So to wrap this up a bit, a good analogy that I like to do is with Newton-Raphson, in the sense that I have an initial guess, That initial guess will give me a sort of orientation of where I want to go. And remember, this is important. This is an analogy. This is not like, again, not a cooking recipe. So that initial guess will orient my second iteration, and so on and so forth. So by the end of the day, I'll have a solution, a potential solution of many that can be. So Newton-Raphson can help to find one of the roots, but imagine this is more like a polynomial problem, and actually it has billions of possibilities. This is a single possibility that I found that can fit the solution. And the second stage of the process that we haven't talked about, stress-strain diagrams yet, would be to start, now that we have our general idea of what we want to achieve, then we can start by modifying the geometry of that initial guess, or that, not initial guess, that solution that we found previously with the topological optimization. So at this point, what I'm doing is that I am exploring which parameters I can change. I can make it taller, I can make it longer, I can make it smaller, etc., etc., etc. And then I will be testing these models on finite element analysis, so I can determine which one will be the more resilient, in the sense that which one can absorb more energy based on stress. And by the end of the day, I'll be doing the same iterative process of, okay, I have my initial guess, then that initial guess will send me to a second iteration, first iteration, and so on and so forth, until I find the right solution for my problem. In this case, the problem will be, how can I create the chassis of a drone that can lift the payload, and at the same time land, like it can help as a landing gear, the same like arms of the drone, and be as optimal as possible, in the sense that no redundant geometries. And thank you for your time. That's everything I have for you today. And again, this is a very superficial video. It is only meant to be a spark to trigger more curiosity, and we will have many more talks about this and go into more detail so I can guide you better. Have a very pleasant day.